Hello friends, in the last class we saw some of the rules of block diagram algebra wherein we studied what are cascaded or series elements, what are parallel elements, what is the summing point, what is the takeoff point, and finally we saw the feedback form of the block diagram wherein we arrived at the closed loop transfer function. For this canonical form of a closed loop control system, this block diagram or the transfer function for this closed loop control system is given as numerator. You have forward block elements gs upon gs is the forward block element divided by 1 plus or minus. Now this plus or minus, remember last class I told you, this plus or minus will be there when I have feedback as minus or plus. If the feedback is plus or minus, here I'll have 1 minus or plus. Minus or plus or minus gs into hs. This we have to remember as a rule for converting the minor feedback loop into a single block, right? Uh, Let us quickly go to the next rule, that was okay. If you look at the closed loop transfer function of this feedback control system, CS is the control variable, that is output, divided by reference input, that is the input. So output by input is the transfer function, is equal to GS upon 1 plus or minus GS into HS. Remember this very carefully. The denominator of this closed loop transfer function, I repeat, the denominator of this closed loop transfer function, when it is equated to 0, what is the denominator of this closed loop transfer function? 1 plus or minus gs into hs is equal to 0 is called as characteristic equation of that system. What I said, the denominator of the closed loop transfer function, this is my closed loop transfer function of a feedback control system, it is equated to 0, it becomes the characteristic equation. Now, why this is called as characteristic equation? See, even though I have written GS HS here, so GS corresponds to some transfer function in S. It will be, let us say, some polynomial in S, maybe S plus 1, S plus 2. That factor will be there at GS. And the denominator, I'll have the factor S plus 1 into S minus 2. Something like that. When I actually derive the equation, when I put it in the block diagram, and when I simplify that block diagram, I'll get the transfer function as, this is the representative symbolic forward block element transfer function, and this HS corresponds to feedback element transfer function. When we actually solve the problem, I'll have maybe S plus 1 divided by 1 plus or minus S plus 1 into S minus 2. Okay, when I equate this equal to 0, that becomes the characteristic equation, as I said. Now this denominator, just for this example, 1 plus or minus S plus 1 into S minus 2 or S plus 2, whatever it is equal to 0. When I solve this, I'll get a polynomial in S. Okay, maybe S square plus 3S plus 2 is equal to 0. Now that polynomial in S talks about the characteristic of the system, or it talks about character of that system. What do you mean by character of that system? When I solve that a polynomial in S, please be attentive and listen to me very carefully. When I get a polynomial in S, as I said, S square plus 3S plus 5 is equal to 0. And when I solve that polynomial in S, I'll be getting, maybe if it is a second order equation, I'll get two values for S. Now these two values of S, when I plot those on the graph, that is called as a pole zero plot, that goes to tell me about for what value of S the system is going to remain stable, for what values of S the system is going to be unstable, and for what values of S the system is going to be stable. So it tells me about the character of the system. Or now these S, if you just recollect, we had taken one spring mass dashboard system example. Just recollect, go back to few lectures. We had derived one equation for spring mass dashboard system. If you remember it, that CS by RS for that spring mass dashboard system was equal to 1 upon maybe ms square plus bs plus k. Now that ms square plus bs plus k is called as is equal to 0 is called as the characteristic equation of that spring mass dashboard system. Please be attentive. Now when I divide the entire equation, what is the equation? Just take a piece of paper and note it down. ms square plus bs plus k is equal to 0 is the characteristic equation. When I divide the equation throughout by m, what will be the equation? S square, m gets cancelled, s square plus b by m into s plus k by m is equal to 0, isn't it? So when I solve this equation, I'll be getting s values, simple polynomial in s, second order polynomial. I'll be getting two values of s, and those two values of s will be corresponding to some values of k and some values of m and some values of b, because the equation is s square plus b by m plus k square plus b by m into s plus k by m, isn't it? When I solve it, I'll be getting s is equal to some values related to b, m and k. Now when I say that for my spring mass dashboard system to operate smoothly, to operate in a stable manner, I can tell the designer about what values of K, stiffness K, what values of B, and what values of mass the designer should use so that the system remains stable. Please listen to me very carefully. As a designer, from this mathematical analysis, from this characteristic equation, I can predict for what values of spring stiffness K, for what values of damping coefficient B, and for what values of representative mass, the system, the suspension system will operate within the stable range, and when it will become unstable, when it will become critically stable, all those values of M, K, and B, we can suggest to the designer, so that once that suspension system is designed, and if the values of B, M, and K are selected within our specified or designer specified range of values, when it is actually manufactured, when it is actually used, I'll be getting stable behavior of that suspension system. Like that for each of the physical systems. This characteristic equation help the designer in selecting appropriate parametric values corresponding to that system. If it is an electrical system, what should be the resistance value, what should be the inductance value, what should be the voltage value, what should be the current values, those also we can suggest. What should be the capacitance values we can suggest, so that that electrical circuitry would be behaving in a stable manner. So for that electrical system also, I can get one characteristic equation. For that pneumatic system also, I can get characteristic equation for that pneumatic system. For a thermal system, I can get one characteristic equation. And from those values of parameters we are getting from the parametric equation, from the characteristic equation, we can suggest to the designer, don't go beyond these values of these parameters. If you go beyond, the system is likely to be stable for this kind of input. So, in other words, we are predicting the system behavior before building the system, just from the equations of operation of that system, from the mathematical model of that system, from the transfer function of that system, from the characteristic equation of that system, I can suggest the designer the range of values of various parameters related to different components. So this is why the name characteristic equation is given to this denominator of the closed loop transfer function. Okay, let us come back to canonical form of feedback control system. What I had said, canonical form, when in a block diagram, if I have one block in the forward path and one block in the feedback path, I call this form of block diagram as canonical form of feedback control system block diagram. This is the canonical form. This is the reference input. This is the feedback signal B. This is the error signal. This is the feed forward block G. C is the control signal. H is the feedback signal. G is the direct transfer function or forward path transfer function. H is the feedback transfer function. G into H is loop transfer function or open loop transfer function. We have to remember these terminologies. Okay. C by R is the closed loop transfer function or control ratio. C by R for this system is G upon 1 plus or minus G into H. E by R is called as actuating signal ratio or error ratio. Actuating signal ratio or error ratio. So E by R is equal to 1 upon 1 plus or minus G into H. And B by R is called as primary feedback ratio. B by R is called as primary feedback ratio. That is equal to G into H upon 1 plus or minus G into H. So B by R primary feedback ratio is equal to G into H upon 1 plus or minus G into H. So these terminologies we have to remember. Questions might be asked based on these terminologies. Okay. Let us go further. One more definition, unity feedback system. What you can see, I have a regular block diagram, only the feedback block is missing, H is not there. So when there is no block, no transfer function H in the feedback loop, this is called as feedback loop. This is the forward path, this is reference input, this is forward path, this is the control signal or output, and this is the feedback path. In the feedback loop, when there is no block of H, we call it as that H has a value of 1, and that when H is equal to 1, we don't have any block. We call it as unity feedback system. So even if simple line is there, we call it as unity feedback system because H will be equal to 1. A unity feedback system is one in which the primary feedback B, this was the primary feedback B, is identically equal to the controlled output C. Same controlled output because there is no H or H is equal to 1. This is called as a unity feedback system. Now, reduction techniques, rules of block diagram algebra. The first rule we already discussed, we'll quickly go through. Combining blocks in series or combining blocks in cascade. G1 and G2 are two blocks. When these are combined, we just multiply it and replace it by one block, G1 into G2. Second rule, combining blocks in parallel. Now, what are the parallel blocks? These are G1 and G2 are parallel blocks. I have one path, forward path, going to a summing point. I have one more forward path joining at the summing point. So what will be the equivalent block diagram? G1 plus G2. G1 plus G2. So this block diagram can be replaced by this block diagram having G1 plus G2, G2 in a single block. This is rule number 2. Moving a summing point beyond a block. All these rules, friends, we have to remember. Moving a summing point beyond a block. Now this is the summing point. I have a block inside this loop. This is on the forward path. Now I want to move this summing point beyond a block, or I want to take this block outside of this summing point. This is what is meant by moving a summing point beyond a block. I can take this summing point beyond a block. Yes, here equivalent block diagram is given. I have taken this summing point beyond a block, but I have to make a necessary change. Here in the feedback path, there was no block. So here in the equivalent block diagram, I have to insert G so that the overall meaning or overall equation relationship of the original block diagram remains the same. Right? This can be proven very easily. So if I'm moving a summing point beyond a block, I have to insert the same value block in that feedback path. So rule number 4, moving a summing point ahead of a block. Now, in the earlier case, I was moving the summing point beyond a block. Now, in the next rule, I am moving the summing point ahead of a block. Or, in other words, I am taking this block inside the loop. I am taking this block inside the loop, like this, isn't it? Earlier, this block was outside the loop. Here, my loop is there, control loop is there here. So, and this block is outside my control loop. I want to take this block inside the control loop. So that is moving a summing point ahead of the block. So the equivalent block diagram suggests I have taken this summing point ahead of a block like this. I have taken the block inside, but in the feedback path, I have to insert 1 by G so that overall relationship is restored. All these rules you have to remember, friends. Rule number 5, moving a takeoff point behind a block. Moving a takeoff point behind a block. So the takeoff point is like this. This is the takeoff point. So in other words, taking the block inside the loop here also. Moving a takeoff point behind a block. So when I want to move this takeoff point here, I can move this takeoff point here, but I have to put 1 by G in the feedback path. Here, the original feedback path, no block was there. When I have moved this takeoff point beyond a block, I have to take 1 by G in the feedback path. And rule number 6, moving a takeoff point ahead of a block now. So right now in the original block diagram, I have in the forward path, I have one block and I have takeoff point here. If I want to move this takeoff point here ahead of a block, or I want to isolate this block G from my loop like this. I want to isolate this block G from my main loop. What I need to do in this equivalent block diagram, it is given when I move this takeoff point ahead of a block. I move this takeoff point ahead of a block like this. What I need to do, I have to put this G value in the feedback path. So these rules we have to remember. Now, all these rules are called as rules for block diagram, rules of block diagram algebra. In your final exam, there can be questions. What are the rules of block diagram algebra? A theoretical question might be asked. You have to draw these sketches and name the rules. You have to draw the original block diagram. You have to draw equivalent modified or reduced block diagram. Okay, eliminating feedback loop. This we already discussed. The canonical form of this feedback loop. I want to convert this into a single block. What I need to do? Single block, 2 blocks are removed and single block is placed. Forward block element G upon 1 minus or plus. Why minus or plus? Because here it is plus or minus. It is to be converted into minus or plus G into H. So if H is equal to 1, if it is a unity feedback system, this is the canonical form, one block is there. If H is equal to 1, what will happen to this equivalent block diagram? G upon 1 minus or plus G into H was there, so instead of H I got 1. So G upon 1 minus or plus G. Now rule number 8, swap with 2 neighboring summing points. See, this is the original block diagram where 2 summing points are there, summing point A and summing point B. Now this rule is valid when there is no block between the summing points. When there are no blocks between the summing points, no block between the summing point, I can swap. I can just exchange. I can bring B. I can bring B here. I can move A here. The swapping of summing points. This is possible only when there are no blocks between the summing points. So this swapping is possible. Now B is moved here, B is moved here, and A is moved here. This is called as swapping, just changing the position. So this is possible in the block diagram reduction technique. Now these are the consolidated list. You can take a printout and remember these rules of block diagram algebra. Now the equations, what you can do as a homework is see whether this equation is restored or not. Whatever rules we have discussed. See here, I'll just tell you a few examples. Originally, this is the blocks in series or blocks in cascade. Original, what is the equation for this original block diagram? How to read this block diagram? X into P1 into P2 is equal to Y. X into P1 into P2 is equal to Y. So X into P1 into P2 is equal to Y. Now when I combine this, the same equation should be obtained. Okay. X into P1 into P2 is equal to Y. Even in parallel case, original parallel blocks are there. I am converting them into equivalent block diagram. So what is the rule here? X is going here inside X into P1. It is going to the summing point. The same X is going here also. X into P2 is coming here. So what is coming here? P1X from this side plus P2X. P1X plus P2X is equal to Y, isn't it? So P1X plus P2X plus or minus. P1X plus or minus P2X is equal to Y is the original equation. P1X plus or minus P2X is equal to Y is the original equation. Now here, when I combine these parallel blocks, what I am doing? X into P1 plus or minus P2. So P1 plus P2, X into P1 plus P2 is equal to Y, isn't it? So if I take X common here, P1 plus or minus P2 into X will be the equation. So same equation is restored. So for all the rules, these equations should be maintained, that you can verify at home. Okay. Okay, the same rules are suggested here. When I move the summing point ahead of a block, 1 by P, whether you call it as P, Q, G, H, these are all conventions. Different books will have different names, but the meaning remains the same, or the logic remains the same. The rules remain the same. Okay. So these were the laws which we can use. These are also called as transformation theorems, which are used for reducing a complicated block diagram, and those can be simplified. And using these rules of block diagram algebra, we can reduce the complicated block diagram and we can obtain transfer function. Now, what are the rules of reduction of complicated block diagram? This is very important, friends. What are the steps? This we have to practice and remember. The block diagram of a practical feedback control system is often quite complicated. It may include several feedback or feed-forward loops. It may include several feedback or feed-forward loops and multiple inputs by means of systematic block diagram reduction. Using various rules of block diagram algebra, every multiple loop linear feedback system may be reduced to canonical form and transfer function can be obtained. The following general steps may be used as a basic approach in the reduction of complicated block diagrams. So be attentive. What is step number 1? Combine all cascade blocks using transformation 1. That is rule number 1. Combine all parallel blocks using transformation 2. Rule number 2. Step number 3. Eliminate all minor feedback loops using transformation 4. Step 4. Shift summing points to the left. Remember this step. This is also important step. Shift all the summing points. If I got number of summing points, shift all the summing points to the left and all the takeoff points to the right by using the rules. And takeoff points to the right of the major loop using transformation 7, 10, and 12. Repeats all these 4 steps 1 to 4 until the canonical form is obtained. Until the canonical form has been achieved. Until a canonical form has been achieved for a particular input. What is the canonical form? So I have got 12, 15 blocks arranged at various locations. I can use the rules of block diagram algebra and convert those into single block in the forward path and single block in the feedback path. So that is called as canonical form. So repeat steps 1 to 4 until the canonical form has been achieved for a particular input. Repeat steps 1 to 5 for each input as required. Now, till now, whatever systems we have seen were single input and single output system. In actual real life control systems, I might have multiple inputs and single output, or multiple inputs and multiple outputs. Those are called as multiple input, multiple output systems are called as MIMO system, M-I-M-O, multiple input, multiple output. single input, single output system is called as SISO system. SISO, single input and single output. Multiple input, single output. MISO, multiple input, MISO, multiple input, single output. Now that multiple input and single output system can also be reduced by using rules of block diagram algebra. For that, this step says repeat steps 1 to 5 for each input as required. And then whatever outputs we get for different inputs can be added together by using principle of superposition. That will clarify by taking appropriate examples. Now let us take one example in this class, and thereafter the coming classes will have more problems for practice so that we can understand the concepts. Now what is the question? Reduce the block diagram to canonical form. Canonical form means one block in the forward path and one block in the feedback path. How many blocks are there? I've got R as the input and C as the output, right? 1, 2, 3, 4, 5, 6 blocks are there. And forward path, I've got 5 and one feedback path block is there. So what is asked? Reduce the block diagram to canonical form and obtain C by R, isn't it? So by using rules of block diagram algebra, I need to convert this into a single block in the forward path and single block in the feedback path. Okay. As per our methodology just now we discussed, step 1, combine all cascade blocks using transformation 1. What are the cascade blocks here? G1 and G4 are in series or in cascade. So these can be combined to get G1, G4. So what will happen? These two blocks will become G1, G4. Okay. Combine all parallel blocks using transformation 2. Parallel blocks. See, parallel blocks. Forward path. Okay, forward path. These are coming to a semicolon. So these can be combined to get a single block. You can remove this entire loop by replacing it by G2 plus G3 block, isn't it? So this entire loop with summing point will vanish down in the next step, isn't it? So these two blocks will become single block of G2 plus G3. Here G1 and G4 will become G1 into G4 as a single block. Now what will remain now? In this minor loop, now this is called as major feedback loop. The outwardmost feedback loop is called as major feedback loop. And the loops within are called as minor loops. Now feedback, now this is not a feedback loop. Be attentive here. This is a forward path and this is the feedback path. So this is a feedback loop, minor feedback loop. Here also we have a loop, but both are having the same direction. This cannot be called as feedback loop. The feedback loop, the directions of signals are different. Forward is this direction, backward is feedback is this direction. Here both are having forward path. So these are parallel paths. This is not a feedback path. Okay. So next step. Eliminate all binary feedback loops using transformation 4. Right. This binary feedback loop, these blocks can be converted into single block by using the rule of removal of feedback loop. What is that rule? Numerator forward block element G1, G4 upon 1, because the feedback is positive, in the denominator I'll have 1 minus forward block element transfer function into feedback loop element transfer function G1, G4 into H1. So this will be the equivalent block diagram by removing minor feedback loop. Now this, friends, you cannot just see and understand. You have to take a piece of paper and use this, digest these rules properly and keep on drawing using each rule, draw the equivalent block diagram and then combine all these equivalent blocks together to form the final answer. Okay, shift the summing points to the left and take off points to the right of the major loop using transformations 7, 10 and 12. Okay, and then repeat steps 1 to 4 until the canonical form has been achieved for a particular input. This is how we get two blocks. This is a parallel block combination, feedback block combination, and one block in the feedback path. Now when once again, these are in series or these are in cascade. These can be combined by multiplying. This is what is done. So what has happened now? In the original problem, there were 6 blocks or 5 blocks in the forward path and 1 block in the feedback path. In the reduced block diagram, 1 block in the forward path and 1 block in the feedback path. This is what is called as the canonical form. And because there is only one input, Had I got one more input, I would have solved it for that input also. Repeat steps 1 to 5 for each of the input as required. Now here there is only one input, so we can stop here. So this is my canonical form. If in the same problem, it is asked to find out transfer function C by R, what I need to do? I need to remove this feedback loop also. So what is the rule for that? C by R will be equal to, in the numerator, forward block element, this entire block will be there. And in the denominator, 1, because negative feedback is there, 1 plus this forward block multiplied by this feedback block H2, this multiplied by this. So this block C by R will be equal to this block. You have to rewrite this divided by 1 plus this into this will be C by R transfer function. I think we'll stop for this lecture, friends.